Hello everyone. Today we are going to discuss the topic open Newton-Cotes formulas which can be used to approximate a definite integral. In the previous lecture we discussed the closed Newton-Cotes formulas. In that case, the endpoints of the interval are included as nodes in closed Newton-Cotes formula. But in the case of open Newton-Cotes formula, it do not include the endpoints of A, B as nodes. That is, we are not using the points A and B in this formula. So here in open Newton-Cotes formula, we are using the nodes xi equal to x naught plus I into h for each I equal to 0, 1, 2, 3, etc. up to n, where h is equal to b minus a divided by n plus 2 and x naught equal to a plus h. That is actually, we know this is, if this is the interval AB, we are taking x naught as the this point. That is, let this be the point h, and x naught, this we are taking this as x naught. That is, n a plus h is equal to x naught. And before that, we are subdividing this entire interval into n plus 1, n plus 2 subintervals. That is, we are dividing this into n plus 2 subinterval. That is x naught, x1, x2, etc. And we are taking this as xn, and this is xn plus 1 actually. So we are excluding these points a and p. So this implies that xn is equal to b minus h. That is, each of these subinterval is having length or distance h. So xn is equal to b minus h and x naught equal to a plus h. Okay. So where h is equal to b minus a divided by n plus 2. That is, it is equal parts. So we are dividing this interval into n plus 2 equal parts. So, and we are ignoring this region. That is, we are ignoring this point A and this point B, endpoints of this interval. In this case, in open Newton-Cotes formula. And here we are labeling this A as x minus 1 and this B as xn plus 1. So x minus 1, this is x naught, x1, x2, etc. xn plus 1. And we are not using this xn plus 1 equal to b, and x minus 1 is also not using. As we can see from this here figure, that is, we are dividing this into n plus 2 equal parts. This is 1, this is 2, 3, etc. up to n plus 2. Up to this we have n plus 1 and this is n plus 2. So each of these are having the length of h. So and we are taking the first point x naught as this point, and we are not ignoring or not excluding this point, not including this point A, and this point B is also not including. So first point will be x naught, then x1, then x2, etc. xn will be this point, which is b minus h. So this is the actual this blue lined curve is actually our actual curve, and y equal bnx is this line. So the open formulas contains all the nodes used for the approximation within the open interval AB. That is, open formulas used all the nodes within the open interval AB. That is, all these nodes are used. Okay, these are in open interval, right? So this formula become integral a to b f of x dx is equal to integral x minus 1 to xn plus 1. We have taken a as x minus 1 and represented b as xn plus 1. So this is integral x minus 1 to xn plus 1 in the f of x dx is approximately equal to this summation I from 0 to n ai f of xi, where ai is the integral a to b li of x dx, where li is the nth Lagrange polynomial of f of x. So we can approximate this integral like this. Now we have a theorem. Suppose that summation I from 0 to n ai f of xi denotes the n plus 1 point open Newton-Cotes formula with x minus 1 as a and xn plus 1 as b, and h is equal to b minus a divided by n plus 2. There exists sigma belongs to the open AB for which this integral is equal to this value. That is summation I from 0 to n ai f of xi plus this, that is h power n plus 3 into fn plus 2 of zeta divided by n plus 2 factorial into integral minus 1 to n plus 1 t square t minus 1 into etc. t minus n dt. That is if n is even and f belongs to Cn plus 2 of AB. That is if n is even, this integral can be approximated with this value, and this will be the error term. Okay, this will be the error term. That is, the error term involves the n plus 2th derivative. That means the degree of precision of this approximation is n plus 1 if n is even. And if n is odd, we have the integral a to b f of x dx is equal to this value summation I from 0 to n ai f of xi plus this, and this is the error term, that is hn plus 2 into fn plus 1 of zeta divided by n plus 1 factorial into integral minus 1 to n plus 1 t plus t minus 1 etc. t minus n dt, where zeta belongs to ab. So if n is odd, we can approximate this integral like this, where the error term will be this. That means this error term involves n plus 1th derivative. Therefore, the degree of precision is n itself. So and also here we have this integral is actually with, here is t and here is t square. So the error term is different when n is even and n is odd. So from the above formulas, we can see that the error, degree of precision, if n is even, the degree of precision is n plus 1, because here we have a n plus 2 derivative in error term, and in error term, or if n is odd, in error term we have n plus 1 derivative so of f. So degree of precision is n, and here is n plus 1. So we have a note. Notice as in the case of closed methods, we have the degree of precision comparatively higher for even methods than for odd methods. We have here uh, degree of precision is n plus 1 when n is even, and when n is odd it is n. So it will be higher. When n is even, it will be higher. Now we can discuss some of the common open Newton-Cotes formulas with their error terms. That is, when n equals 0, we have the midpoint rule. That is, when n equals 0, the open Newton-Cotes formula is this: integral x minus 1 to x1. That is, this is actually x minus 1 is a and x1 equal to b. So integral a to b f of x dx is equal to 2 into h into f of x naught plus h cube divided by 3 into f double dash of zeta, where zeta lies between x minus 1 and x1. That is, zeta lies between a and b. So here, when n equals 0, here we have this is, therefore we can say that this integral is approximately equal to this 2 into h into f of x naught. That is integral x minus 1 to x1, or a to b f of x dx is approximately equal to 2h into f of x naught, and this will be the error term. The error term involves the second derivative, so the degree of precision is 1. Degree of precision is 1 when n equals 0. We have noticed that when n is even, the degree of precision is n plus 1. So n is equal to 0 is an even number, so degree of precision is 1, n plus 1. Now the second one, when n equal to 1, we have the formula as this: integral a to b, because we have when n equal to 1, we have this is x minus 1, then x naught, then x1, then x2, then x3. x3 is b and x1 is a, and we have when n equal to 1, we are subdividing this, where h is equal to b minus a divided by n plus 2. That is, b minus a divided by n plus 2 means divided by 3. So we are dividing this into 3 equal parts. So this is x, this is 1, this is 2, this is 3. Yeah, this is b here. So we have x minus 1 to x2. This is x minus 1 to x2 here. This is b. So we are excluding this a and b, that is x minus 1 and x2 we are excluding. So we need only these 2 points, x0 and x1. So the integral becomes 3h divided by 2 into f of x0 plus f of x1 plus 3h cube divided by 4 into f double dash of zeta. Here this is the error term. Therefore this integral a to b f of x dx is approximately equal to 3h by 2 into f of x naught plus f of x1. That is this, and this is the error term. So here also we have in error term it involves second derivative of f. We have the degree of precision is 1. Here n equal to 1 is odd, so degree of precision is n itself, that is 1. Now when n equal to 2, we have in the integral x minus 1 to x3, that is x minus 1 and x3 we are ignoring, that is h is equal to a b minus a divided by n plus 2. N plus 2 is 2 plus 2, that is 4. So our interval will be of this form. This is a, this is b, and this is x minus 1, this is x1, x naught, x1, x2, and x3. So we are subdividing this into 4 parts. So we can take this as b, right? And we are excluding this x3 and a. So integral, this is x minus 1, so integral x minus 1 to x3 means integral a to b f of x dx is equal to 4h divided by 3 into 2 into f of x naught minus f of x1 plus 2 into f of x2 plus 14 into h power 5 divided by 45 f4 of zeta, where zeta lies between a and b. So we are using this f of x1, f of x0, f of x1, f of x2, that is x0, x1, x2 we are using. So we have this integral a to b f of x dx is approximately equal to this value, and this will be the error term. So in error term, it involves f4, that is fourth derivative of f. So the degree of precision is 3. You know, n equal to 2 is even, so degree of precision is n plus 1, that is 3. And when n equal to 3, we have h is equal to b minus a divided by n plus 2, that is 3 plus 2 is 5. So the interval will be like this. This is x minus 1, that is a, then x0, x1, x2, x3, and x4. x4 will be our b. And we are excluding this a and b. We are using only x0, x1, x2, and x3. f of x0, f of x1, f of x2, and f of x3. So integral a to b f of x dx will be equal to this value, and this is the error term, and therefore we can say that this integral is approximately equal to this value when n equal to 3, where zeta lies between x minus 1 and x4, that is a and b. That is zeta belongs to open AB. So here error term involves fourth derivative, that is degree of precision is again 3. When n equal to 3, you know it is e odd, so degree of precision is n itself, so that is 3. Now we can discuss an example. Use the open Newton-Cotes formulas to approximate the integral 0 to pi by 4 sin x dx is equal to 1 minus root 2 divided by 2, which is approximately equal to this value. The same question we are used in the previous lecture to use the closed Newton-Cotes formulas. So here now we are going to approximate this integral by using open Newton-Cotes formulas. So we know the open Newton-Cotes formulas are this. When n equals 0, we have the midpoint rule, that is integral x minus 1 to x1 f of x dx is equal to 2 into h into f of x naught plus h cube divided by 3 into f double dash of zeta. So we have this integral is approximately equal to this value, 2h into f of x naught. So here when n equals 0, we are dividing the interval where h is equal to b minus a divided by n plus 2, that is 2. N equals 0 here, so b minus a divided by 2, that is pi by 4 minus 0 divided by 2, that is pi by 8. So pi by 8 is h, so 2 into h is 2 into f pi by 8, so sin f of x naught. X naught is actually we have this x minus 1 as 0, x naught equal to this is x minus 1, that is 0 is a, so x minus 1 plus h, so this is that is a plus h equal to x naught. So this is actually pi by 8, and next one is b is equal to pi by 4. So we are using only this point x0, so this is sine pi by 8 because x0 equal to pi by 8. So 2 pi by 8 into sine of pi by 8, which is approximately equal to this value, 0.3050558887. So this is the actual value of the integral. So to obtain the approximate error, we can subtract this. That is, this minus this will obtain the error. Now when n equal to 1, we have the formula as this: integral a to b f of x dx is equal to this. So we are using x0 and x1, the values of x0 and points x0 and x1. So here what is h? H is equal to pi by 4 minus 0 divided by n plus 3, n plus 2, that is 1 plus 2 is 3, that is pi by 12. Pi by 12 will be h. So we have x0 is equal to pi by 12, that is x0 is equal to a plus h, where a equal to 0 and h equal to pi by 12, and x1 is equal to then this x0 plus h, that is pi by 12 plus pi by 12, that is 2 pi by 12, that is pi by 6. So this is pi by 6. F of x1 is sin pi by 6, f of x0 is sin pi by 12, and 3 divided by 2 into h is pi by 12. So approximate value will be this. This actually this is equal to this value. This is the error term. So for approximation, we have ignoring this. So this integral is approximately equal to this value. So it is this. Now when n equal to 2, we have integral minus x minus 1 to x3. That's integral a to b f of x dx equal to this. So this integral is approximately equal to this 4h divided by 3 into 2 into f of x0 minus f of x1 plus 2 into f of x2. And this is the error term. So for this we have h is equal to b minus a, that is pi by 4 minus 0 divided by 2 n plus 2, that is 2 plus 2 is 4, that is pi by 16. So this is h. So we have x naught is equal to 0 plus h, that is pi by 16. x1 is equal to this pi by 16 plus pi by 16 h, that is 2 pi by 16, that is pi by 8, and x2 equal to pi by 8 plus h, that is pi by 16, that is equal to 3 pi by 16, 3 pi by 16. So we have f of x0, f of x1, f of x2 as this sin pi by 6, f of x1 is sin pi by 8, and f of x2 is sin 3 pi by 16, and here h is equal to pi by 16. So applying these values, we get approximate value as this: 0.29285866. Now next formula is when n equal to 3, we have the formula is this. In that case, we have h is equal to pi by 4 minus 0 divided by n plus 2, that is 5. So pi by 20. This is h. So x naught is equal to 0 plus pi by h, that is 0 plus h, that is pi by 20 itself. So f of x naught is sin pi by 20. x1 is equal to pi by 20 plus pi by 20, that is pi by 10, that is f of x1 is sin pi by 10. F of x2, that is x2 equal to then pi by 10 plus pi by 20, that is 3 pi by 20. So we have f of x2 equal to this 3 pi by 20, and f of x3 equal to, again we are adding pi by 20. So we have 4 pi by 20, that is pi by 5. Okay. So from this we get this is approximate value. Approximate value of this integral is equal to this, and this is the error term. We have to we don't want to use this. So applying these values, we get the approximate value as this. So these are the approximate values by using open Newton-Cotes formulas. Now we can summarize these results with the approximation errors. This is actually the same question we are used in the previous lecture by using closed Newton-Cotes formulas, and for that we obtain these values. When n equal to 1, we have the approximate value is this. N equal to 2, this is the approximate value, and n equal to 3, this approximate value, and when n equal to 4, this is the value. So the corresponding error will be obtained by subtracting this approximate value from the actual value. So we obtain this as the corresponding errors. And in the open course formulas we used in this lecture, we obtained these as the approximate values when n equals 0, 1, 2 and 3. This is when n equal to 3 we obtain this 0.2928693. This is the one, and this is 0.29285866. This is when n equal to 2, etc. So to obtain the approximation error, we can just subtract this value from the actual error. We have the actual value is this of actual value of the integral is this. So if you are when n equals 0, we are obtained this as the approximate value. So when we subtracting this value from this, or we are using the absolute value of this minus this, we get the value this 0.0076665, and in last one we can subtract this from the actual value this, so we'll obtain the error this. In a similar way, we can just verify all the other errors.